All right, everyone, grab a seat and let's get started. Welcome to today's Explainer. I am absolutely thrilled you're here because today we're going to act like true physical chemists. You know, for way too long, undergraduate organic chemistry just feels like an exercise in brute force memorization, right? You get this massive chart of aromatic substituents, you're told, hey, some are activators, some are deactivators, and you just kind of have to memorize where they direct new molecules on a benzene ring. Well, not today in my class. Today, our goal is to master the actual underlying physical chemistry behind predicting reactivity and orientation in benzene rings. No more rote memorization, I promise. To kick things off, I want you to consider the question right here. Why is it that simply attaching a hydroxyl group, an OH group, to a benzene ring suddenly makes it react 1,000 times faster in an electrophilic substitution reaction? I mean, what invisible molecular machinery is driving that massive acceleration? Just keep that in the back of your mind as we go. Because the sheer scale of the difference we're talking about is literally staggering. If we set standard benzene right in the middle with a baseline rate of 1, notice what happens when we swap that hydrogen for an activating OH group on the far left. Boom, the relative rate is 1,000. But then look on the far right. Swapping it for a nitro group drops the rate to 6 times 10 to the negative 8th. It becomes over 10 million times less reactive. That is an absolutely wild range of speeds. So here's our syllabus for today's Explainer. We'll start with a substituted benzene puzzle, then unlock the uranium ion, compare induction versus resonance, dive into ortho and para activators, tackle the halogen exception, and finally wrap up with meta-directing deactivators. All right, part 1, unlocking the uranium ion, the rate-limiting bottleneck. To really get into the fundamental mechanism dictating these massive speed differences, everything, and I mean everything, revolves around this definition, the uranium ion. When an electrophile attacks a substituted benzene, it forms an intermediate. Now, this isn't just some fleeting, unimportant moment. It is the rate-limiting step. It's the bottleneck. So the absolutely crucial point here is that the uranium ion is a positively charged, delocalized carbocation. And because it carries that positive charge, its stability directly dictates how fast the overall reaction can actually proceed. Which brings us to a golden rule of chemical kinetics. The transition state resembles the rhenium ion. Basically, if you want to speed up a reaction, you have to lower the energy barrier, the transition state, to get there. And since the transition state looks and acts so much like our positively charged rhenium ion, anything that stabilizes that positive charge is going to automatically lower the energy barrier. Make sense? These energy profiles illustrate that concept perfectly. Trace that blue curve in the middle. That's our baseline benzene. Now follow the green curve. Adding an electron-releasing group, what we call an activator, pumps electron density toward that developing positive charge. It stabilizes the uranium ion, dropping that activation energy hill, and the reaction accelerates. Conversely, look at the red curve. That's an electron withdrawing group. It pulls electrons away from an already positive charge, which destabilizes it, creating this massive energy hill that slows the reaction down to a crawl. Moving on to part 2. Induction versus resonance, the forces at play. So we know we need to stabilize the positive charge to speed things up, right? But how do substituents actually push or pull these electrons? Well, we have 2 competing forces at work, inductive effects and resonance effects. The inductive effect is our chemical pull of electron density through the sigma bonds, all based on electronegativity differences. The resonance effect, on the other hand, is the push. It's the donation or withdrawal of electrons through pi bonds, typically using lone pairs. Every single substituent on a benzene ring is basically playing a microscopic game of tug-of-war between these 2 forces. Part 3. Ortho and para activators, stabilizing the charge. Let's see how these forces dictate not just the speed, but exactly where the incoming electrophile attaches. Take the nitration of toluene here. Trace the ortho and para pathways. Those are the top and bottom ones. Notice those boxed resonance structures? In both cases, the positive charge lands directly on the carbon attached to the methyl group. That is a tertiary carbon. The methyl group's electron-donating inductive effect perfectly stabilizes that localized positive charge. But if it attacks the meta position right there in the middle, the positive charge misses that crucial tertiary carbon entirely. Now, this effect completely amplifies when we look at phenol, which has that highly electronegative oxygen from our opening question. Inductively, sure, oxygen pulls electrons away. But through resonance, it pushes its lone pairs right into the ring, massively outcompeting the induction. Take a look at the box structures for the ortho and para attacks. the oxygen lone pair drops down to form a double bond, creating a fourth, highly stable resonance structure where every single atom has a full octet. The meta-attack pathway completely lacks this stabilization, and that is exactly why an OH group is incredibly fast and specifically acts as an ortho/para director. Which brings us to part 4, the halogen exception, a chemical tug-of-war. All right, time for everyone's favorite curveball in organic chemistry, the halogens: fluorine, chlorine, bromine, iodine. They are uniquely frustrating until you apply our first principles. Halogens represent a literal chemical clash. They're highly electronegative, creating a really strong inductive pull that starves the ring of electrons, making them overall deactivators. They actually slow the reaction down compared to standard benzene. However, their lone pairs give them a weaker electron-donating resonance effect. It's kind of a paradox, right? So how do we resolve this paradox? Look at the mechanism for chlorobenzene. Yes, the reaction is slow overall because of that inductive withdrawal. But when it does happen, check out the boxed structures. Just like we saw with phenol, the chlorine's lone pair stabilizes the positive charge exclusively in the ortho and para intermediate pathways. The meta pathway gets absolutely no help. So they are deactivators, yes, but they are uniquely ortho and para directors. Part 5, meta-directing deactivators, nowhere else to go. Finally, let's look at strong deactivators, like that nitro group we saw way back at the start, which actively push the incoming electrophile away from the ortho and para positions. Here, there's no tug of war. Inductive and resonance effects violently reinforce each other to withdraw electrons from the ring. If an electrophile tries to attack the ortho or para positions, it creates a resonance form that places a positive charge directly on the ring carbon bearing the strongly deactivating group. You are essentially forcing two positive charges right next to each other. It is an incredibly unstable situation, meaning the meta position wins completely by default. It's just the path of least resistance. So here it is, your ultimate takeaway study guide. But instead of just rote memorizing it, you actually understand the why behind the rules now. You know an OH group is an ortho/para activator because that oxygen lone pair drops down to stabilize the positive ammonium ion. You know why halogens are the weird middle child, strong inductive withdrawal but helpful lone pair resonance. You've officially mastered the physical chemistry governing these reactions. But before I dismiss the class, I want to leave you with a provocative thought. Everything we did today assumed we started with just one substituent on our benzene ring, but what if you start with a ring that already has a strong activator and a strong deactivator? Who wins the chemical tug-of-war then? I want you to keep applying those first principles, think about the uranium ion stability, and I'll see you in our next explainer to tackle exactly that. Class dismissed.